depression is quote unquote a real thing or just something society's made up. I don't subscribe to that belief, but this idea of what happiness or sadness really is actually quite variable around the world. So anyway, we see in the general population these kinds of lateralized effects of affect that we can map on to approach and avoid behaviors. We also see that in clinical populations who have some abnormal emotional functioning, and that's something we briefly touched on last lecture, I believe, that one of the really sort of applied angles for this kind of stuff, not only does emotion color virtually all cognition, if you want to understand why people make the decisions they make, the emotions they're feeling at the time can be really relevant. Inducing an emotion, one emotion as compared to another, can radically change someone's decision making. But in addition to kind of in the normal population, the typical quote unquote population, emotion being relevant for lots of stuff, we know that in things like depression, in things like anxiety, in things like psychopathy, in things like post-traumatic stress disorder, a large part of the symptoms and effects, at least from one perspective, can be understood as relating to dysregulation of emotion. So we see things like people who are depressed seem to have an overactivity in their right prefrontal cortex, not only when they're explicitly saying they're not feeling good, but just at baseline. When you damage the left frontal cortex, like with a motorcycle accident or something, depression is a common symptom. We see situations where babies that cry more or less, that are sort of quote unquote more or less fussy, seem to have a distinction in their how active their right hemisphere is at baseline. Seems to be the case that those babies that seem like they maybe are less content based on operationalized as crying more frequently or for longer durations, seem to have this asymmetry going where they have greater activity in the right hemisphere, just like when you induce it in participants in a transient kind of way. So again, just to kind of wrap all this, not wrap it up, but just to kind of summarize what we're talking about, it does seem a lot like emotion can be understood, even though we think of it as this, potentially beautiful thing that adds richness to our life, which it certainly does. From an evolutionary perspective, it makes a lot of sense to think about emotions, and in particular, the positive and negative affect that is related to different emotions that can encourage approach as compared to avoid behaviors, is maybe in large part all about survival. And again, things like avoiding a predator that might be a threat, but being attracted to food that looks good when you're hungry. A lot of this stuff can come down to survival. This is maybe a bit of a stretch too, but in our complex modern society, we could argue that things that make us feel good, doing something for an hour that you really genuinely enjoy, can be very important for stress reduction. And so even things that might seem like, how could this be adaptive from an evolutionary perspective? Like, how could watching a couple episodes of a sitcom that you like, that can't evolve. We haven't had sitcoms for very long. But finding things that you enjoy, that maybe lift your mood when you need it, that maybe reduce your stress level when you need it, even if we can't directly connect that to a specific threat in the ancestral environment or potential reward, even just, it's like a, what's the word? Like an escape valve for steam that's building up in a system that'll cause damage if the valve isn't opened. So we can even think about, again, what we would think of as modern pleasures that can't possibly on the surface be connected to evolutionarily based stuff, might also have some kind of survival advantage just by helping you get through your day. So I think I've sort of connected the dots pretty explicitly. I probably don't need to say in writing here that maybe fear-based responses we can understand as being related to half of this approach avoid kind of dichotomy. Maybe being afraid or seeing that someone else is afraid, which cues you to a possible threat in the environment, might help modulate your behavior in a way that allows you to survive for a little bit longer. So that sort of in the simplistic form we've told up until this point kind of makes sense. But one of the big wrinkles here is essentially the very same wrinkle that I introduced, I believe, cognitive control, the topic of cognitive control with. And that is, we live in big, complex worlds with a lot of moving pieces, basically an endless number of things that you could do. You'll never, none of us are going to live long enough to do every possible thing in this world that we could do. Um, so there's so many options. Even if the world doesn't change, even if it freezes and stays static just as it is today for the rest of our lives, we'll never get through all the possibilities that we could engage with. And then when you factor in that the world's always changing, what used to be bad can be good, what used to be good can be bad. There's a great deal of uncertainty and moving pieces, and humans need to be adaptive, and humans need to be able to flexibly adapt their behavior to changing environments and changing circumstances. And we've seen in other contexts that there are lots of neurological mechanisms that allow us to flexibly change our behavior. So one of the things that we need to do is not only become afraid of things that maybe rightfully should scare us because they're threats to us, and we need to pay attention to that and maybe change our behavior accordingly. But equally important in this complex, ever-changing world is the ability to flexibly change your learning and change the associations you make. Maybe when you were a kid, you hated school, and at some point it started becoming more interesting to you. That happens to a lot of us. I always hated school, sort of growing up until I got into university. And then I probably in part because I started studying things that were more interesting to me and maybe were presented in a way that I could engage with more deeply than in high school. All of a sudden, school and the topics that are, the focus of classes in some cases became interesting to me. And so I may have over many years, like many of you perhaps, developed very negative associations with school that changed partway through my life when my circumstances and environment changed. So we need to be able to not only learn these kinds of fear-based responses, and of course we could extrapolate that to other kinds of examples, right? We need to learn how to, get excited when we see things that might be potentially rewarding to us. It's also important for us to unlearn those associations when they're no longer relevant. And of course, in the context of classical conditioning, that really has to do with extinction. That's all about, if you learn to associate the sound of a bell with food, and thus the sound of the bell on its own comes to make you salivate, just like the food at one point by itself made you salivate. If you keep hearing the bell ringing enough times when it's not paired with food, that's no longer predictive of food. And so we see extinction kick in. And so that dog who has learned to salivate in response to the bell will lose that association. So that's extinction, if you've forgotten. And I sort of just gave you the formal definition here. It's when the conditioned stimulus and the unconditioned stimulus are no longer presented together, so you no longer come to associate them. So in the context of fear-based response, that would be like if you play an A note on the piano, every time you deliver an electric foot shock, that becomes acquired at one point, that becomes learned. We could measure freezing behavior when you just hear when the piano note is played by itself without the foot chalk. But if we play the note by itself without the foot chalk enough times, extinction will kick in. And so at one point, people kind of thought, well, that's just like forgetting, right? Forgetting has been explained in different ways, right? Originally, it was this idea the memory just decays. It's like water evaporating. You just lose it. It falls apart. Maybe that's something physiological. Maybe the synapses fall apart if they're not used. But we now, in the context of conditioning, we now think of extinction as actually more of an active process. It's a relearning of a new association, not simply the dissolving of an old association. And we see that there are interesting situations like spontaneous recovery, where even if the dog, the salivary response to the bell is extinguished, You might do it 100 times and it never salivates, and on the 101st time after extinction, it does salivate. You see these learned responses occasionally kind of poking their heads out, kind of the tip of the iceberg, so to speak. And you see relearning. You see that if then you try to get it to reacquire an association that had been previously extinguished, the learning is much more quick. The learning is it's acquired much more rapidly than if they were starting from scratch. We also see that, remember, NMDA receptors, we talked about briefly as being kind of a neurotransmitter subtype that is going to be very important for long-term potentiation, and as a consequence, very important for learning associations between things, and certainly is relevant for acquiring classically conditioned responses. We see that, for example, if we use like knockout techniques or other kinds of methods like antagonists to block the activity of these receptors, extinction doesn't happen. All of these things really suggest that, again, it's an active process where you're changing the association or maybe just learning a totally new association. It's not the case that you just forget the old association, which sort of bolsters even more this idea that extinction is actually an active process. Humans, that someone who has learned, for example, a classically conditioned response, if you're in a battlefield, loud noises are usually related to, or often related to, threats, right? Think about gunfire, think about bombs, think about explosions of various kinds. And as a consequence, if you're a soldier who's deployed in a war zone, you tend to very quickly learn. And there's some explicit controlled learning here, but there's also surely in some of these situations, a classically conditioned association that gets learned. We see that soldiers will, have triggering stimuli that in a war zone is just like seeing your buddy across the campfire look scared, indicating maybe that there's a bear approaching that could be a threat to you too. Hearing an explosion in a war zone is an indication that you need to very quickly appraise the situation for danger because there's probably a threat. And that's absolutely appropriate in a war zone. And probably the people who don't do that do not have a great survival rate. It's absolutely adaptive in that environment. But of course, the problem is if you come back to, if the war zone wasn't your home, if it was your home, but then you move somewhere else, if you're now all of a sudden in a place that's not a war zone, those associations may be so strong that if you hear a car backfiring, something that even sounds similar to, for example, a gunshot, or maybe if you hear an explosion on television, even if you know it's television, that association can be so strong. That's in part what people talk about when they talk about triggering stimuli. And we could think about a whole range of other kinds of traumatic experiences that could result in lots of different kinds of triggering stimuli being in someone's everyday environment. And so, of course, it's easier said than done, but kind of the point here is if these people could just efficiently extinguish these associations, and of course, it's not something that's under conscious control. But if it's almost like telling someone, tell your FFA not to respond when it sees faces, right? Tell your amygdala to just chill out when something happens. You don't have direct access to these things. As we'll see, we think you do have some control over emotion, and it can be an uphill battle. Modifying your responses, it's possible, but sort of the point is, even though it's not something that we have direct access to, and even though it's not something that we can perfectly control, in theory, if in this example, a soldier was able to just flip a switch and turn on the extinction function in their brain when they left the war zone, it wouldn't be a problem. But of course, because they don't have direct access to that, this creates huge problems, which again underscores this idea that relearning new associations and unlearning, even though that's not really what happens, inhibiting previously learned associations is maybe a better way to put it, is tremendously important. So we've got a couple more things to run through today, but the next stretch is going to look at first the rodent brain and then some equivalencies in the human brain that we think are involved in this kind of approach of avoid sort of architecture. So we've got a nucleus in the amygdala that we think is important in initially acquiring the association, right? So when you first learn that the foot shocks are going to accompany the sound of a particular note on a piano, right? The amygdala is going to be important. The next few slides really are going to focus on these two parts, the infralimbic cortex and the paralimbic cortex. So you're going to see this abbreviated as IL and PL. So, and all doesn't really matter, maybe I'll do this just to be a little bit more consistent. We think that, and so this is in the rodents, and so sort of this graphic is going to be in the top right-hand corner of the next few slides, so you'll have plenty of opportunity to look at this. But we're basically looking at the IL and the PL in the rodent brain, and we're going to speculate that they might be equivalent to functions that are being served by the dorsal anterior cingulate cortex and the ventral medial prefrontal cortex in humans. And essentially, we think that if you're in a situation where you've already acquired a fear-based response, and then you learn a new fear-based response, remember, we don't think it's the case that the old fear-based response just goes away. We think that you learn a new response as well. But again, because of things like spontaneous recovery, or some of the other stuff we talked about in the last slide, we also think that that association remains. It's not overwritten. Think about if you're writing something in Word or Pages, you can use the save as function, and that saves a duplicate version. So if you're editing a document, you can maintain the original draft and then save as, and you have an edited second draft. That's different than the save function, which just overwrites the original file. So think about maybe this as not being like the save function, but like the save as function. You're learning multiple you're acquiring multiple associations. So control comes into play, because if you have multiple associations with a stimulus, then you need to, on some level, decide if you have one fear-based association and one neutral association, you need to maybe decide which you're going to activate. And both might be activated to a certain extent. It might be back to this competition thing where there are multiple signals and the strongest signal is going to win. So infralimbic cortex seems to be involved with kind of boosting the signal from the more recently learned association. So in our example, let's imagine you've got a foot shock that gets learned to be associated with a tone, and then eventually the tone becomes associated with a light turning on. So the light turning on should be neutral, right? The foot shock is aversive. So if you're expecting a foot shock, that's gonna produce a fear-based response. But if you're just expecting the tone to signal the onset of a light turning on, that's neutral. You shouldn't have a fear-based response. So if you initially learned the fear-based response, then you acquired a neutral association with that same sound, the infralimbic cortex would be involved with kind of pushing the perspective that your response should be neutral. It's prioritizing the more recently learned association. Paralimbic input is going to be involved with prioritizing or pushing the originally learned response. So it's like the part of your brain that's advocating or arguing for, you should be scared. This is a stimulus that you should be afraid of. The IL is kind of arguing or pushing the perspective that this stimulus is neutral, you should not respond. So why do we think in the first place that the IL cortex is involved with trying to kind of boost the more recently learned association, the neutral association in this example that we just went over on the last slide? So if you lesion IL, it doesn't prevent extinction. So remember, you sort of learn extinction. There are extinction trials where you repeatedly present the stimulus that you had originally associated with something negative without that negative association anymore. So you can sort of say extinction happened. You can measure whether it happens and how long it takes for for it to happen? How long does it take before the fear-based response, so something like freezing behavior, which we talked about on a previous slide, maybe the first few times you play the sound without the foot shock, they still freeze for just as long. Maybe the 10th time you do it, they're only freezing for 2 seconds instead of 4 seconds. Maybe the 20th time you've done it, they're not freezing at all. So that's kind of how you would operationalize, okay, they've extinguished that response. Or another way to put it that's kind of confusing linguistically, but is sort of the same thing, is, or maybe not, depending on how you think about these things, is you've learned a new association that's now neutral. So we see that even though lesioning these neurons doesn't prevent extinction, it does seem to be the case that in animals that have had IL lesion, they don't seem to carry over that extinction learning to the next day. So on day 2, it's as if they didn't learn the new association. They're still afraid. They're still freezing just as much, even though towards the end of day 1, they seem to have learned the neutral association. So this suggests, of course, that they did learn it on some level. It was affecting their behavior on day 1, but it's almost like the difference between, it's almost like when you successfully encode a memory, but you have trouble retrieving it on a test. It doesn't mean that it's not in there, but it's not being activated at the right time. So this finding is kind of suggesting, again, that the IL cortex isn't so much involved with learning extinction or learning a new neutral association. It's involved with, again, prioritizing or pushing or arguing for that association to be what you actually feel or what guides your behavior. It's also the case that those neurons didn't respond to the original tone, or, well, it's the same tone, right? It's the designation changes because it comes to be associated with different things, but it's that same piano key or whatever you want to do. These neurons don't seem sensitive to the tone on day 1, but on day 2, they are responding to it. They seem tuned to a certain extent to respond to it, which is weird because, remember, on day 2, there was no behavioral evidence for extinction that carried over from day 1. Their freezing behavior that stopped on day 1, which suggested that they had learned the fear-based association was no longer relevant. On day 2, that behavior wasn't evident. So they're not acting on the new association, but again, it kind of looks like the association is represented in some way in IL because these neurons are actually now sensitive. It's like they're listening to and noticing when that tone gets played. They're just, for whatever reason, not successfully kind of conveying the message. It's like they register the response, oh, we don't have to be afraid, but they don't tell the rest of the brain we don't have to be afraid. So remember, these are animals that have had this part of the brain lesioned. One thing that's pretty cool, and we've seen this kind of correlation between neural activity and some behavioral measure in a few other examples, but the extent to which those IL neurons become active when they hear the tone played from day 1 on day 2. So we might have some rats where these neurons become really active when they hear the piano key, some that are just kind of active, some that are not active at all. That is a good predictor of the amount of freezing behavior they have. For those rats, it was inversely correlated. So for those rats that had a lot of activity in those IL neurons, they responded really strongly to the tone. It affected their freezing behavior a little. It did affect their freezing behavior. For those that, the CS neurons might have become just barely active, but not really when they heard the tone on day 2, there might have been a smaller change in freezing behavior. If there was no activation in IL neurons on day 2 when hearing the tone for a given rat, there might be no difference in their freezing behavior. So it's as if the amount of activity, the more activity in IL, the less the behavior originally associated with the fear-based response comes out. And vice versa. If these neurons are not active, then the original fear-based behavior comes out very strongly. Again, sort of supporting the idea that when this becomes active, it's prioritizing the new neutral association and saying, don't worry about the old fear-based response. But if this region doesn't become active or doesn't become sufficiently active, it's not going to sufficiently impact freezing behavior. Again, it's like the signal is It's like the judgment is made that we don't need to be afraid, but it doesn't tell the rest of the brain. There's some signal that's not being sent out, or not being sent out in the same way or as efficiently. So back to PL, we think that the PL, which again, in the example we've been using, um, would be related to prioritizing the original fear-based association. We see that, for example, if you try to deactivate that region, either temporarily with lesions or other kinds of methods, you see that the original fear-based response doesn't seem to be there anymore, or doesn't seem to manifest. So playing that tone doesn't really induce freezing behavior anymore, even if that was the originally acquired association, if this part is damaged or again just temporarily deactivated. I'm going to do the middle one in a second, but this is kind of the complement, the other side of that. You can deactivate the region, and it reduces freezing behavior, for example, but stimulating that region increases freezing behavior. So it's sort of the opposite of the IL. It seems like when the PL becomes active through microstimulation or just naturally, the originally acquired fear-based association comes to influence behavior. If it's not active, if it's inhibited in some way, then you don't get that original fear-based response influencing the behavior to the same extent. We also have this neat sustained firing correlation. And so, of course, we've talked about that. Specifically, we're talking about that in regards to working memory, but it's come up a couple times. So for example, if a monkey is holding the location of a target in mind after it's disappeared off the screen because they know they'll get rewarded if they can correctly identify where it was, we see prefrontal cortex neurons becoming active and continuing to fire until they make their response. It's like the neural representation of what they're holding in memory. And we see that neurons in PL cortex have sustained firing patterns that temporally line up pretty nicely with other behavioral indicators of fear behavior. So for example, if you get freezing behavior that lasts for 10 seconds, you might get PL in that particular rat that freezes for 10 seconds in response to whatever it's been conditioned to. You might see PL neurons continuing to fire for about 10 seconds after exposure to, for example, a piano key. So it seems like, again, it's correlational, we don't know, but it seems like maybe activity in this region and prolonged activity extended over a period of time influences behavior, fear-based behaviors over an extended period of time that lines up temporally very nicely with the duration of continued firing. So that's the rodent brain. We think that there's kind of a, it's never really a direct equivalence. And you think about all the other things that prefrontal cortex and the ACC have been associated with in our course, right? That are maybe not things that these two regions in the rat brain are necessarily associated with. But we do think we can kind of draw a reasonably direct comparison and say the VMPFC is maybe doing the job of the IL in the rodent brain, and the DACC in the human brain is maybe more or less doing the job of the PL in the rodent brain. And so we get the same kind of associations that you might expect. So you get, in the VMPFC, you get increased activity during fear conditioning. Or sorry, this is the opposite actually, because this is the other one. This is what is prioritizing or encouraging the more recently formed association. So that would be like the extinguished fear-based response. So we see that activity is actually reduced in that region when fear conditioning is being learned, but it spikes, it increases in activity during extinction learning. As well as in situations where we can infer that the humans, because we're talking about humans in this case, we're probably retrieving new associations. We get a similar kind of correlation as I talked about in the last slide, when you get humans who are trying to inhibit previously learned associations. You can predict. So for example, if I tell you, and this isn't about classical conditioning, but for a simple example, if I tell you, I want you to press the A button, the button on the left of the keyboard, every time you see a picture that you judge to be of a living thing, like a human or an animal, and I want you to press the L button, the button on the right side of the keyboard, every time you see a picture that is inanimate, like a chair or a desk or a house. Imagine we do a bunch of those trials. You get really used to that button mapping. You can think a little bit about the IAT we talked about on Tuesday if you want to. But you get really used to pressing A when it's animate and L when it's not. But then what happens if halfway through they say, okay, we're swapping the mapping, and now we need you to press the opposite. We need you to press L every time you see something living. And so what you have to do is inhibit a previously learned association, because you have this tendency, you want to press A because you've gotten really practiced at pressing A when you see living things. So for the first few trials, you have this prepotent response. You start to press A, or you start thinking about pressing A, you inhibit that, and you say, no, I have to press L. So that's not related to conditioning or fear. But this is an example of inhibiting an old association. And we see that the degree to which you're successful behaviorally at inhibiting an old association. So think about how you would infer that. If after you swapped the button mapping and you used to have to press A to identify something that was living, now you have to press L to identify something that was living. If on the first few trials after you swapped the button mapping, you saw the response times increased, and then after a few trials, or maybe more likely a block or two, they went back to what they were before the button mapping changed, that would be a way to behaviorally infer, oh, they're having trouble, there's interference, they're slower to make their response, presumably because they're having trouble inhibiting. So you can make inferences behaviorally, even if people don't make quote unquote mistakes, by actually fully activating and acting on previously learned associations. You can still sometimes see evidence that they're struggling, like they slow down. So you can see that, if this region has more activity, you see that they have less evidence for difficulty inhibiting old associations. We can do some connectivity analyses with fMRI and see, or rather, this is structural. So this is just probably with MRI, or maybe DTI even. You see that the cortical thickness is different. There's a correlation related to an individual difference in how efficiently you can extinguish or inhibit previously learned associations. People who have greater cortical thickness in this region, the VMPFC, seem better able to flexibly shift their behavior and act on that new button mapping without getting interference from the previous button mapping. Or we could, that's, again, the example we use, but we could extend this to other kind of extinction learning. Someone who had more or less cortical thickness, if they had, imagine I had a TV once that gave me electric shocks. And so every time I would try to turn it, it would give me an electric shock. And so eventually that stopped, but I for a while became really weary of changing the angle on the TV because I just expected to be shocked when I touched it. And eventually that stopped, and I eventually stopped being nervous, but it took a while. So you would see that, that feeling of nervousness in people who had maybe a greater cortical thickness would go away more quickly. People who had thinner, who had more cortical thinning or less thickness, same thing. You would see that it would take longer for that kind of nervousness to go away. And the ACC, which we've talked about lots recently, we think kind of is a sort of an analog to the PL in the rodent, in the human brain, the dorsal anterior cingulate cortex, we think is. So we see that activity in that region correlates with skin conductance. You might not realize it, but you start sweating just a little bit more or less when you get slightly more or less nervous. We can often tell when we're sweating a lot, but we don't really have any insight into these micro variations in the amount that we're sweating usually, but you can pick that up with the right instruments. And we see that people who have more activity, or in situations where you have more activity in that region, you start sweating a bit more. You see that if you show people aversive aversive unconditioned stimuli, like for most people, snakes or spiders fit that description. The region tends to just like faces kind of light up, quote unquote, the fusiform face area. We see that aversive kinds of like pictures of stuff that people tend to find aversive tend to light up the ACC. This last one's kind of interesting too, because it fits in very nicely with our idea of an error signal. This idea that one of the things the ACC is doing, and probably other parts of our brain as well, is modeling, trying to predict what's going to happen in the environment and keeping track of whether those predictions end up being accurate, right? You get an error signal if you try to make the right response, but you're told that you press the wrong button as per the task rules. Or we talked about error signals in the context of possibly predicting expected rewards for both yourself and another player in a game, that when the predicted reward does not line up, or when the delivered reward does not line up with the predicted reward, we see error signals. And we've talked, not tons, but it's as I say, come up a few times, and I've tried to really help you sort of think about error, the way that even a handful of a few error signals, or just one, might be a way that behavior is shaped and might have a big role in learning. So we see that when you have a conditioned stimuli that's presented without the expected unconditioned stimuli. So like if you play that piano note, but the foot shock is no longer delivered, we see that the DACC gets active. And that might be an error signal that is plotting the deviation between what was expected and what was delivered. And that error signal could be really important for extinction. If the DACC becomes active enough times because you felt sure that something bad was going to happen after a certain stimulus was presented and it wasn't. If that happens enough times, extinction happens. That's what we just talked about. And maybe part of one of the mechanisms that drives that is maybe this error signal. Maybe in brief, if you were programming a couple lines of code to try to convey this idea, maybe it would basically be, if the error signal is above X, more than Y number of times, erase this association. Or, as we talked about, they don't really get erased, they get deprioritized. So it would be, sort of relegate or keep this association, but kind of tag it as, maybe going to be relevant in the future, but right now it's not an actively relevant association. That's one possibility. So, and I think I'll leave the last 4 slides. I'm going to say a couple words about this one that set up the next 2 slides. And then we have one really quick experiment to talk about, looking at the effect of meditation on the attentional blink. So you'll remember the attentional blink from our lecture on the cognitive neuroscience of video games. If you haven't listened to that yet, or you don't remember, check that out for an explanation for what the attentional blink is. We're going to see something very similar to the benefit that action video game players had in the attentional blink after participants go through very extensive meditation training. So I've sort of already given you kind of the punchline for the last couple of slides. But then the next 2 slides, which I guess we'll start on Tuesday before rolling into language, the next topic, sketch out kind of a complicated model. We're not really going to talk about it in a huge amount of detail, but it brings together a lot of pieces of the brain and a lot of processes like attentional filtering, like attentional selection that we've looked at in different contexts that might in conjunction allow us to modulate our emotions. Because the discussion so far has really been about these kind of automatic, rapid, probably more or less implicit association processing that happens, like with conditioned fear, like with judging trustworthiness, like with perhaps racial biases that might influence judgments related to things like trustworthiness. And we haven't talked at all really about conscious control of emotions. And particularly when we think about the problems in various clinical populations that emotional dysregulation can lead to, being able to control emotions has some really obvious benefits. And of course, within a non-clinical population, simply feeling good more often and feeling bad less often, I think appeals to everyone. You don't have to have a clinically relevant problem to appreciate that having control of your emotions can improve your quality of life. So how do we go about controlling our emotions? The model that is on the next couple slides is largely going to take a lot of, or at least borrow a lot of the stuff that was built to explain cognitive control in general, as directed to controlling your emotions, which probably makes a lot of sense. So as I said, things like attentional selection, what are the targets that you're trying to pay attention to? Attentional filtering, what are the distractors that you're trying to ignore? Think about in a testing situation, if you actually know some of this stuff and you want to get it down on the exam and you want to get marks for it, and you start worrying that you're gonna, make a mistake, or you're gonna say something wrong, or you're gonna say something stupid, and you start spending some of your exam time worrying rather than focusing on the content, right? This is a prime example of how having better attentional selection mechanisms, which help you focus your attention on the actual question and the content and your understanding and memory of the content, and filtering out those negative thoughts, those nagging kind of worries, we can understand how that could really benefit your performance, let alone, not to mention, make you much more comfortable. So